test, test. 1, 2, test, test, test. Test, 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 test. Test, test. Test, test, test.
네, 한번 말해볼래? 오케이.
1, 2, 1, 2.
오케이.
테스팅 하나 둘.
Test.
Hello? Yeah.
But where is the other?
It is so fun.
It's not.
And trying the mic. Can you hear me? Sounds good.
Can you hear me? Test, test. That sounds excellent.
Good to go? Yeah. Huh? Okay. We're going to get started. So good morning, everyone. My name is Ariel Kellison. I'm from Gawa, and I am super happy to be chairing this session at PLDI 2025 on type systems. So we have 4 speakers today, and I'm happy to first welcome Catarina Gamboa from Carnegie Mellon University and the University of Lisbon. She is going to talk to us about the challenges developers face when using liquid types. So thank you, Catarina.
But despite their power, most developers, and probably most of us here in the room, have actually never tried them in practice. Why? Well, maybe because the experience can look a little bit like this. So today I'm going to show you exactly what makes liquid types frustrating to use in practice by presenting our study on the usability barriers for liquid types. I'm Catarina Gamboa, and this is a joint work by CMU and the University of Lisbon. So type systems are useful in verification, but sometimes we cannot encode some domain-specific information. But with logically qualified types, or liquid types, we can add predicates to our language, to the types of our language, by saying, for example, that an array needs to have a length greater than 0. Then we can apply them to our functions and verify them at compile time to ensure that our code is following these properties. And liquid types, basically on the background, create these verification conditions that we can send to an SMT solver that will check their satisfiability so that we can see if the verification passes or not. And liquid types have been implemented in several languages, and they have also been used in different use cases, from protocol violations to try to find the security in cryptographic protocols, MVC applications, and database queries. But despite all of these different applications and implementations, the fact is that most developers still are not using them. So our main research question for this paper was, what are the current usability barriers that developers face in adopting liquid types? And when we started thinking about this, we started to think, how can we answer this question? And how do we know what are developers' doubts and decisions and their intermediate steps and difficulties in learning and using liquid types? Well, and the answer is just one. We need to ask developers. So we did interviews and observed developers using liquid types, specifically using Liquid Haskell, which is the most mature implementation of liquid types at the moment. And so we interviewed participants with different levels of experience with liquid types, and also both from academia and in industry. At the end, we got 12 new users that were participants that did not know about liquid types, but already knew about the target language, so Haskell, and several experienced users that had already used Liquid Haskell in one of their projects. And for all of them, we did different qualitative research methods, such as interviews, observations, retrospectives, and using think aloud protocols. So how does our study look like? Our study design starts by having people sign up and tell us if they already used Liquid Haskell or not in the past. If they didn't, but if they already know Haskell, they are our new users. And so we introduced Liquid Haskell to them with a short tutorial of 30 minutes. Then we asked them to do a final exercise where they had to mix different parts of using liquid types, from writing them to reading them, also fixing them in different parts, and implementing code that respected the liquid type. At the end, we did a small interview to understand what were the challenges that developers faced and also their overall experience. For experienced users, so participants that had already had projects using Liquid Haskell, we started by doing an interview to try to understand what were the pain points, but then we also thought it was important to focus on a project where they used Liquid Haskell to anchor their experiences in the code and also make them remember other different parts that they did not remember for the interview. Then, if the experienced participant had a project at the moment that used Liquid Haskell, we actually asked them to work in that project for around 30 minutes while we observed. And they would work like our master, and we were the apprentices trying to understand what were their thought processes and how they were gonna go about their work. If they were not using Liquid Haskell at the moment, so the project probably already finished a while ago, we asked them to do a retrospective, and so to try to understand again what they did in their project and show us the most interesting parts. So overall, we did a study with those numbers of participants that I mentioned before, and we came up with 9 adoption barriers overall. All of them were shared between our participants, and interestingly, all the problems mentioned by our new users were also mentioned by our experienced users, but in different levels of complexity. But there were some other specific parts that were only mentioned by our experienced users, given that the code that they were using was more complex and they had more time to experiment with it. We combined these all barriers in 3 main parts. So the first one is verification challenges, where we have then clear divides between Haskell and Liquid Haskell, confusing verification features and unfamiliarity with proof engineering. Then we have developer experience challenges that are a little bit more related to unhelpful error messages, limited IDE support, complex installation and setup, and some insufficient learning and reference resources. And finally, we have some scalability challenges that include some limitations of automation and manual proof flexibility, and also scalability and solver limitations. And I'll now walk through some of the examples of each one of these categories. So starting with the verification challenges, let's start with a simple example. You don't need to understand all the code, but this is basically a function that has these front and back lists, and then has to create a new list where everything follows through. And we gave this exercise to our participants. Actually, we just gave them the implementation without the specification, and they were very puzzled with this implementation. From the start, they were like, this is interesting. We have only one base case, only for front. So where's the base case for back? Doesn't really make sense. So it actually only makes sense if we also look at the specification, the liquid type, where we say that B is also a list, but that has the size of exactly the size of F, the first one, plus 1. And so if it's always bigger than the first list, then we just need one base case. And this was very interesting, because they were expecting this part to be in the implementation, but now it is in the liquid type. So it actually shows that there is this symbiosis between the liquid type and the implementation, where some changes in the code might be required or might be possible because we have the accessible to both those parts. Actually, one of our participants also really felt like they had to change the Haskell code to fit into the verification. They mentioned that they found themselves writing code in certain ways or found the code being written in certain ways to convince the proof assistants that were necessarily not the most intuitive for them. Also, our participants think that liquid types can do this middle turn between a very good type system, but they don't really have to, or a full type system with dependent types, for example, where they don't need to have a doctorate degree to understand what's going on. But still, you need to have an intuition of what's going inside the liquid types. And so you still need to identify what are the pre and post conditions, what are the requirements that you have for your programs, and what predicates you need to write to ensure that the properties hold. One of our participants, for that example that I showed you before, the rotate example, they mentioned that I think if I had to come up with a type of rotate by myself, trying to figure out this invariant should be quite difficult. As a small fun fact, we did try that in our pilots, and just that exercise went more than 30 minutes, so we decided to drop it and change it for something slightly different. There are also some confusing verification features that I will not go a lot in depth into, but that are related to lifting functions as measures or the mechanics of how the SMT works. As for developer experience challenges, I'm going to show you another piece of code where we have this new type, qn, that actually just uses this qsize function or measure, but does not apply it to a certain element. And so this gives an error. But actually, it gives 3 errors, all in different places from the place where the actual error was made. And so there is this error indirection between where the error appears and the actual location where it should be fixed. Additionally, if you touch in one of these and try to see what are their messages, this is more or less what it shows. Okay, and again, you don't need to read all of this, but if we focus here on the part that it's larger, you can see that we have these variables VV0 and AA2CB that appear nowhere in our code. So they are very helpful for our verification in our internal representation, but if we show this to user, we actually have this code mismatch that we cannot relate their message to the code. One of our experienced participants also mentioned this problem in a different scale. They mentioned, well, tell me what the type error is. No, instead you get a message like 5 is not less than 4. I mean, I know that's true, but what does that mean? Also, even this problem could be a little bit improved by some IDE support. For example, by having some syntax highlighting. But actually, in most cases, we do not have that. And the fact of having these liquid types as comments, that's sort of an emotional thing where you kind of feel that the things that you're writing are fake. So usually, our comments are just to comment things. They are optional. They are not used for verification. So even the simple thing of using comments as the liquid types can endanger the experience of the users. Also, it does not help that some of the compilation and setup can be a little bit difficult. One of our new users mentioned that they tried to use and install Liquid Haskell before coming to our study, and they failed miserably. So that's one reason why they might not be too inclined to use liquid types in the future. When people experience these problems, usually they use the tutorial that's available online, the Slack groups, the GitHub issues, but the community is still small. And the tutorial is very helpful if you're starting out, but when you have more problems with advanced features, it might be a little bit more difficult. As for the scalability challenges, we have this program that we sent to the SMT solver, basically. And we use the SMT solver as more or less a black box, which can be very helpful because you're constantly being supported by it. But also, you need to get to a point where you can automate the proof. So you kind of need to understand what is that point that you need to get to. And that is the challenge. So this brings some of the limitations of automation and manual proof flexibility. Also, when the program and the proof complexity starts to increase, there is also an increase of the compilation time. One of our participants mentioned that at the end, if they ran the whole proof until the end, it would take 5 hours or so, or maybe longer for all the thing to verify. Also, we need to be aware of some of the internal solver limitations. We treat them as black boxes, but sometimes you need to understand a little bit more of what's going inside. So for example, not everything can be converted to the language of the SMT solver, and some things can fail, and you still need to understand why. So overall, we have these 3 categories of challenges that we found, and you might be wondering, are these barriers specific to Liquid Haskell, since we kind of did this study just on Liquid Haskell? So let's go back to some of them. Let's start with this unclear divide between Haskell and Liquid Haskell. Well, actually, most of the implementations that I showed you at the beginning focus on the target language and add the liquid types on top of them. So other liquid types implementations like Flux or Liquid Java might also suffer from some of these problems. Additionally, one of our participants mentioned that for the confusing verification features and unfamiliarity with proof engineering, that they only see their colleagues actually using liquid types as more of a lightweight verification tool and not a full verification, which demands a deeper understanding and finer grained control over the proofs. So maybe viewing them a little bit more as lightweight verification technique can be helpful. As for the developer experience challenges, well, I think there was a talk about Rust in here yesterday that also explored some of these problems. And also the IDE support, even the example that I showed to you about the comments, is shared with other languages that also use the verification in comments. Additionally, for the complex installation and setup, some of our participants mentioned that developers will probably go on their first day on the job and test it. If they can use it in the first 5 minutes, they'll probably use it later on. If not, they'll probably give up and not touch it for at least a couple months. As for the scalability challenges, specifically related to the SMT solver, other tools that will also use SMT solver backends can also be endangered by these problems. So overall, these challenges are not just specific to Liquid Haskell, maybe not even just to liquid types, but listening to our developers, we can better understand what are their struggles. And so together as a community, we can improve the design and implementation of our languages, trying to reduce the usability barriers. If you want to know more, we have our paper, and if you want to participate in our future studies, you can leave your email for future studies. Thank you very much.
All right, thank you, Katarina. And now we'll open up for questions.
Great talk, thank you so much. So you have focused on a specific verification paradigm, refinement types, and even more so specific tools. So now imagine I'm going to build the next awesome verifier that everyone should use. Which things should I look for, and which mistake I should absolutely not make when designing it?
Well, there are many things that we can work on, and this was just like an overview of different challenges that you have to do. I would say that trying to bring the users into the development process from a start could be a good idea. To like try to understand what do you want to verify, how do you want to verify it, and not just build our tools and then ask afterwards if they enjoyed it. So I think that from one perspective, it could be helpful to bring developers or the potential users a little bit more to the beginning of the process, into the design perspective, to understand what could be some of the challenges that they want to fix and how we can overcome those. But then all of the challenges that we mentioned here could be relevant to tackle in different parts of the process.
Well, yeah, I'm more interested about how to bootstrap this exact process, because building verifier is a challenging task, and well, it would be good to know how to get some early feedback, well, cheaply. But this is something that we can discuss offline.
Thank you.
Okay, and please be sure to state your name and your affiliation.
Hi, Leonard from University of Montreal. Really great talk. I had a question. During the study, did you notice like features that users expected should work but wasn't supported by the system?
Yeah. So some of our participants, even for the new users that were not familiar with liquid types, they actually had already used some tier improvers in the past, so they're already familiar with some things. And so they were expecting to have some more manual control over the different predicates that you can use, because they were expecting more of the interactive tier improver approach. And so there were some things that they were expecting to have from that landscape brought into the liquid types, and actually they didn't find them. So there were a few things that can then show you some of them, but there were some of the things that they were expecting because they were already familiar with other applications that were kind of in the similar landscape.
Okay, thank you.
Hi, thank you for the great talk. I'm Hyunri from Seoul National University. So about the problem in IDE support for liquid type language, I wonder the reason why there's a problem in this language is just because of the fundamental lack of enough developer, or is there a fundamental difficulties on that?
So if I understood correctly, so liquid types actually can be very helpful and useful, and even our experienced users that are not using them at the moment would actually use them again if they needed to verify other things or if they were using Haskell. But there are some challenges still that appear, specifically when your program starts to grow and you still need to understand everything that's going on. For example, trying to find what are some of the parts of the code that are sent to the SMT solver and what are not being able to verify, or what's the condition that's missing for you to verify everything, can be a challenge. And so this is overall like a landscape of different challenges that we have. Are those really dependent with the implementation? Some of them might be a little bit, but a lot of them are more generic, and we can just use more research into understanding them better.
Okay, we have maybe time for one short question.
I'm Nayland from Jane Street. You mentioned that like some of your users found it weird to write liquid types in comments, and I'm wondering whether there's like syntax highlighting for those comments, or if there's like maybe some other more native syntax construct you could use to alleviate some of that difficulty.
Yeah, so in this case, our new users were using our tutorial mostly to do everything, and so we did not have any syntax highlighting. Also, in most of the editors that are available, they do not have syntax highlighting at the moment. And we can think of that like, it's very simple, it's something that you can actually do, but people don't. And so trying to understand a little bit of the things that developers might want to have can be very interesting to overcome these simple difficulties that we don't realize that are problems until actually someone tells us that it is a problem. So yeah, I think that's it.
We can thank our speaker again.
Thank you.
Okay, and now we're going to welcome Fritjof Stott from Uppsala University, talking to us about ownership models for dynamically typed languages.
Cool. So before getting started, I want to say that this is joint work with Brand, Sylvan, Matt J, Matt P, Guido, Eric, and Tobias. It is not just me who is presenting this. So the work I'm presenting is a design paper. It introduces a dynamic ownership model which can be retrofitted into dynamic languages. Yes. The work itself is language agnostic, but we have designed it specifically in the context of Python, and with the goal to add true parallelism to Python. Currently, there is one limitation in Python that makes this difficult, and that is the global interpreter lock, also called the GIL. While it prevents breakage by making sure that Python objects are only modified when this lock is held, it also sequentializes programs and makes them slow. This makes sure that the reference count is correct, but it is a really big bottleneck. This is why there's a community effort going on to improve this. One of the big ones is PEP 703. This one proposes to make the global interpreter lock optional. This effort is also commonly called free-threaded Python or no-GIL. You might have heard about it. The second big proposal in the community is PEP 734, which proposes adding subinterpreters which are completely isolated. To share information between two subinterpreters, you actually have to serialize the data and send it to a different subinterpreter. Now that I've given you the context, I will give you an intuition how Python works in these regards and where Langfish comes in. So first, let's take a very simple Python program, a single-threaded one. We can represent the memory as the green area over here, and we have a single thread, which is a thread emoji, which has access to objects. Slight bit to make sure everyone understands. The arrows are references, and the objects are the blue circles. Now, if this thread would want to do some modification, for instance, increment our number by 1, it is super easy. It can just increase it. Not a problem. We don't have any data races. Now, in free-threaded Python, which wants to propose to remove the GIL, we can have multiple threads living in the same memory space. And these, living in the same memory space, are allowed to create references to all objects. And thus, we can have a situation like this. Now, incrementing integers can be hard. So let's try to split the work across 2 threads. And when we do this, and they are both super fast, then we have a data race. And this data race comes down to a central problem of having shared mutable state, in this case, this object. Now that I've given you an introduction of free-threaded Python, let's revert the time a little bit to our number 42 and use subinterpreters. I mentioned that subinterpreters are completely isolated, so they don't have shared memory. And to here split work, you actually create a copy, send it to a different subinterpreter, And now both of them can do the amazing work of adding 1 to our numbers. But we still don't have the result we want. We wanted a 42, and now we have 2 objects, 2 versions of the same object from what we expected with the value 43. And this is where our ownership model comes in. Our ownership model ensures exclusive access to mutable data at runtime, and it is called Langfish. And it is called Langfish because it can work with the GIL, with the global interpreter lock, and without GILs. So before giving you an intuition of how it directly works, with the no-GIL effort, it allows you to reason about data races and prevent them all together, while with subinterpreters, it allows sharing cross subinterpreters without breaking isolation. So let's start this by adding a region. Langfish manages ownership on a region level, so on a group, on an isolated group of mutable objects. You notice that the region, which is the yellow blob in the middle, is not dedicated to one single interpreter or memory region, but it's in the middle. And we have the green object up there, which is called the bridge object. This is inside the region and acts as a handle. Now, we are in a dynamic world, which gives us some flexibility. So to transfer ownership, we actually just have to do a field assignment, and as a side effect of this assignment, as a side effect of creating reference from our bridge object to the blue object, the ownership is transferred into the region. Another change you might have noticed is that the arrows going from the thread into to the objects are dotted. And this is because these are not owning references, these are borrows. This is very similar to the Rust model where it is a reference where you can read, and in this case also always manipulate from, so mutate, but it is not the owning one. The owning ones are solid. Now, let's go through our example again where we want to increment our number. So our thread 1 has right now mutable access, so it could increase the number. However, with Langfish, we can prevent any other thread from having mutable access at the same time. So reference from thread 4 would not be allowed. To actually transfer ownership, to actually allow thread 4 to access it, we have to first remove our references from thread 1, and then we can create new references. Once we have a reference to the bridge object, we can access contained objects and do our magical addition. Now, Langfish is a memory model, and it is concurrency model agnostic. Here I will show you a model how it can be combined with locks to make parallelism and concurrency safe, but there are other concurrency models you could combine them with. So let's introduce our lock here. And since it's a lock, which can be a primitive, a safe primitive, we can have 2 threads accessing it. But critically, right now, the lock is released, so none of them have access to the contained data. To actually do the mutation, they first need to acquire the lock, indicated by the key, and then they can create borrows into the region. Now we can do our addition super easily. In other languages, there's a common problem of what happens when you now release the lock. How with Langfish, we can prevent this. We can specifically detect these things and throw an exception, and saying, if you release the lock right now, there could be a data race because you still have residual references. To actually release the lock, we have to remove all borrows, burn them, and then we release the lock. After we've released the lock, thread 4 can acquire it, also do the addition, and we again get the expected result of 44. Once the reference is removed, we can again release the lock. So now that I've given you an intuition, I wanted to talk about some goals we had with Langfish. First, we wanted to have no concurrent mutation to prevent data races. We wanted to facilitate ownership transfer, and have control over sharing. Another advantage is that we can bound access. So for instance, if you give a region to an external library, you know that it can only access objects in this region. But Langfish wasn't designed in a vacuum. In fact, it was designed in the project for Python. So this comes with certain challenges. One of them is the non-existence of static checking. Typically, ownership models have been predominantly implemented using static type checking, but we don't have that in Python. Python is dynamic, and it can do a lot of things during runtime. It's actually amazing. The next problem is that we don't have type metadata. A lot of other ownership models use type annotation and so on to say where and how ownership might flow, but we don't have that in Python. And the last one, which I think is also super critical, is that there's an existing ecosystem. In theory, you can design the best ownership model in the world, but if it would break the entire ecosystem of Python, it would not be used. It would not be applicable to this case. Now that I've given you an introduction and an intuition, hopefully, of what Langfish does, I also want to give you some limitations which we needed to add to Langfish to make this efficient to implement. For this, we have a thread in our region here, and we can add a subregion. So this is simply a second region, R2, and we are allowed to reference the bridge object with a single reference. As long as this one is unique, everything is fine. But if we would now try to create a reference from C to R, that would break uniqueness. But the good thing about this is we can throw, again, a nice exception explaining that this region is already owned, already referenced, and this reference is not allowed. I want to say this is just about owning references. Borrows to the bridge objects are totally allowed. Another restriction we have is that isolation cannot be broken. So I've mentioned that regions are isolated group of mutable objects, and all references to these objects have to either be borrows or come from inside the region. It is not allowed to create a reference from our C object here to our D object. Now, after the restrictions, I want to talk a little bit about how Langfish can be implemented. So to implement it, we envision using a write barrier. And this write barrier does a few things. One of the things is that it assigns ownership on objects. This is one of the first things I've shown you where the assignment of a field actually transferred the ownership into the region. Then it tracks external uniqueness, and to implement this efficiently, it maintains the local reference count. The local reference count can be seen as the number of borrows going into a region. So you can see right at this moment, our region 1 has a local reference count of 2 because we have 2 borrows coming in, while our region 1 has 2 references coming in, while our region 2 has no borrows and would be safe to send. Now, if we would add a reference going from the thread into our region 2, the write barrier would increase the local reference count, and to prevent the parent region from being sent off, it would also propagate this change upwards. Now that we've incremented the local reference count, the write barrier is also magically able to decrement the count when references are removed, and this that has the same spiel of decrementing the parent local reference count. So, I've mentioned the write barrier. What implication would this have for the actual implementation of the interpreter? Any field assignments like this one, x.f equals y, would have to be slightly rewritten to store the previous value in a temporary value. Then we would call the write barrier, and if the write barrier succeeds, so throws no exception, then the assignment can be done. This write barrier, or this might look like a little bit of a rewrite, but I want to remind you that Python already has a write barrier for reference counting, incrementing, and decrementing. Our paper actually includes a mock pseudocode for the write barrier. This looks like a lot, but the fast path is actually highlighted in green and comes down to 2 if statements, which should always be true, unless you use ownership in some edges, and the reference count increase and decrease. I've mentioned that this is the design paper, and and as part of the paper, we've also implemented FrankenScript, which is a dynamic language with Python-like syntax and semantics. And this one actually generates automatically the diagrams I've been showing you to give you an intuition how it works. This has been invaluable to communicate inside the team and design things. So thus far, I've talked about the design in PLDI. Next steps for us is the implementation. This is a picture of us visiting the US in May to present our work at PyCon US. We have also been in constant feedback with C Python developers. A special shout out to Brand, Giro, and Eric, who have given us invaluable feedback and helped us a lot with our work. The paper, as a design paper, contains a lot. Especially I want to highlight some of the cases you could have because Python is still a dynamic language, and that is handling reflection in mutable types. In Python, everything is an object, even a type, with lots of beautiful cycles. We also have the ownership rules specifically defined, and I encourage you to read it. In summary, we have designed a dynamic ownership model called Langfish. Langfish enforces exclusive mutable access at runtime, tracks ownership for a group of objects, and throws errors before data races can happen. It allows cycles, which is important to support existing topologies, and can be retrofitted into dynamic and gradually typed languages. I've explained this all in the context of Python, but we have also spent a little bit of time considering how it might be applied to other languages. It also can allow true parallelism without substantially rewriting the Python ecosystem. At least that's the work we are doing and aiming for. Thank you very much for the attention, and I'm happy to take any questions.
Please state your name and your affiliation.
Nick Swami, Microsoft. Great talk. There's one thing I didn't understand. In your initial example, you have one of the threads has a reference to a sub-object in one of the regions, and then when it's done with it, it burns it. And now, if I want to regain a reference to that object, do I have to traverse the entire object graph from the bridge object to find it again?
Yes. Right. You would have to do that right now. Potentially, so one of the things is that this is concurrency model agnostic, right? So we enforce complete isolation of the region. There might be some design space to have not weak references, but references that only are active in those cases, but we haven't explored that space a lot yet. Good question.
Thanks.
Hi, thanks for the great talk. Leonard from University of Montreal. I was wondering, if I understand correctly, you have to create those regions manually.
Mm-hmm.
So how big do you think those regions will be once implemented in Python, or what kind of regions do you think you will have?
So this is a complicated question and touches a little bit on something which was not in the talk but is more in the paper, and that is immutability. So if you would always move all types and everything into these regions, they could become quite large. But you can make certain parts immutable, which allows references from multiple regions. And thus you could shrink your regions or share data across regions and only really share the mutable data. So there's room for optimization if you want to. We don't really have an estimate for how big these can be, but we've tried dumping some object graphs of Python objects, and it's surprising how big they can be. At the end of the day, it's also, once you engage with Langfish, you will add parallelism, so the speed up is probably, or should be way above what you get just from these changes.
Okay, can we have the next speaker please come to the front? Sorry, just set up your laptop, yeah.
Yeah.
Do we have more questions? So let's thank our speaker again. Thank you.
Okay.
True tone on.
What?
You have true tone on.
Oh, I didn't turn it on.
Oh, it's off?
It's off.
It's off, okay.
Okay, so our next speaker is Andong Fan from the University of Toronto, and they will be talking to us about formalizing techniques used in practical implementations of type inference algorithms.
Thanks for the introduction. Hello, everyone. Thanks for coming to my talk. My name is Andong. I'm from the University of Toronto. I'm going to talk about practical type inference with levels. This is a joint work with Han from Princeton University and Ning, my PhD advisor. So modern functional languages such as Haskell and OCaml, they have advanced static type systems and rely on sophisticated type inference to infer types automatically and become practical. For type inference, there are many formalizations that describe type inference formally and precisely by declarative specifications and algorithmic formalization. With such formalism, people study the theoretical aspects of type inference algorithms such as their soundness and completeness and so on. Formally. On the other hand, there exist practical implementations of type inference algorithms, and many of them employ various implementation techniques for good reasons such as performance improvement. However, those implementation techniques, they bring a huge gap between the theory and practice of type inference. Such a gap could lead to, first, confusion for implementers who follow the specification, the formal presentation of type inference, and they could only find more efficient implementation techniques later. And perhaps more importantly, this gap could compromise the theoretical guarantees provided by the formalism because those results doesn't directly apply to the implementation because of those implementation techniques. So this paper, we focused on formalizing one such important implementation technique called levels to bring the theory and practice of type inference closer. So we contribute formalism of a type system that incorporates the following language features: state generalization, local data types, and higher rank polymorphism. They are all within a level-based type system framework. And we provide mechanized proofs of the soundness and completeness results of level-based type system in the ROC theorem prover. We also provide a formalization of a level-based and a bidirectional type inference algorithm. And finally, we implemented level-based type inference for the COCA programming language and evaluated its performance. COCA is a research programming language featuring a type and effect type system. So next, I'm going to give you an overview of our formalism that supports late generalization, local data types, and higher rank polymorphism within a level-based framework. Okay, so let's get started with late generalization. Late generalization is an important aspect of Hindemiller type systems, which is the basis of type systems in functional languages like OCaml and Haskell. Let's take a look at the example here of a late binding in Haskell syntax. Here, we define f as an identity function, and it's bound to the body of this late binding expression after the keyword in. Notice that this f is applied to two values of different types, int and bool. And this f as an identity function, it could be used polymorphically without problem. So how could this be type checked? In Hindemiller type system, when we are typing the right-hand side of late binding, here, the identity function, we assign a type variable, for example, a to x, and give the identity function the type a to a. And late generalization kicks in to generalize this type to a universally quantified polymorphic type for a dot a to a. And now this f can be used at different types because a is a universally quantified one, and it can be instantiated to what type is needed. Okay, so to be formal, the formal presentation of Hindemiller type system is as follows. We first type the right-hand side of the late binding, which is U1, type tau1. And here, later we generalize three type variables in tau1 as for a .1 and put it in the typing context. Here, there's an important side condition that requires the type being universally quantified. They should not appear as free type variable in the typing context. This check is crucial for the soundness of the late generalization. But in practice, it also causes significant inefficiency because we have to traverse through the whole typing context to compute all free type variables in it. So let's see an example of level-based generalization, late generalization with level. The idea was originally proposed by Didier Remy in 1992. So here we have a typing judgment form under a typing context psi. We infer the type of V as type sigma. And here we have a natural number n, which is the current typing level. And let's check out the simple example. Here we start with an empty context and infer the type of simple program which binds the identity function to f and return it directly in the lab body. So we start with typing this expression at level 0. And here, to type the right-hand side of the lab binding, which is the identity function, we first bump the level number to 1. And after bumping the level number to 1, we are allowed to introduce a fresh type variable a at level 1 into the typing context and say that the free variable x has a type a. And we infer the type of the identity function as a to a. And to type the lab body, here we get back to level 0, and we generalize the type of f, which is the bound polymorphic identity function, and its type is got generalized at level 1 to be a polymorphic type for a dot a to a, and we infer the type of f as this type. So with that example, we can take a look at the formalism in our system of level-based late generalization. So to type a late bound expression, we first type the right-hand side of lab binding, which is E1 at the level n+1, and it has an infer type sigma 1. And later, to type the lab body, we get back to level n, and we generalize the free type variables appearing in sigma 1, and those free type variables are at level n+1, so those are the type variables that got generalized, which corresponds to our earlier example where the type of f was a to a, right? And we generalized the free type variable a because it was at level 1. And why generalizing type variable at level n+1 is okay and enough exactly? Here, we enforce an important invariant that typing contexts always have levels less than or equal to the typing level. So, the type or the typing context psi, it could only contain free type variables at level less than or equal to n. And as another important property, the infer type of sigma 1, which comes out at the level of typing n+1, and this sigma 1's level can only be less than or equal to n+1. So all the free type variables appearing in sigma 1 at the level n+1, they are free in the context. Okay. So next, we take a look at another the next feature of our system, which is local data types. So consider this example. Here, we define a binary tree data structure that is constructed by leaves of integer values and nodes of subtrees locally. This tree data type is bound only after the keyword in. Here, we pattern match on a node value and return a string on both branches of the match. Overall, this expression returns a string value. And notice that this tree data type is only valid locally after in and not outside of this data expression. On the other hand, if we return a leaf value directly, then the expression as a whole, it returns a tree value which goes out of its scope. So this one is rejected. To model this behavior, we have this in the level-based system, where we first put the type constructor T into the context, and it's at level n+1, and so that when we're typing the expression E, we can use the type constructor at level n+1 in the E. And here, notice that we again bump the level number to n+1. And in the return type of this expression, which is sigma, we have a side condition that requires this sigma at level at most n, so that it could not refer to the local data type T, which is at level n+1. And this level check on the return type, it could be implemented smarter as is implemented in OCaml type checker. It can be a constant type lookup. Okay. And finally, the last feature of our system is higher rank polymorphism. So as an example, consider a lambda expression where the input is annotated as a polymorphic identity function type. And in the body, this f is applied to both int and bool. And the type of this lambda is so-called a higher rank polymorphic type, because there is a universally quantified type for a.a2a appearing on the left-hand side of the arrow. To type check such a program, we need this kind of subtyping or subsumption relation here, which says that the type sigma 1 is more general than the type sigma 2. And the most important rule in the subtyping relation is these two rules, which compares two polymorphic polymorphic types. The type on the left says that if we compare a type sigma 1 to be less than another type with a universal quantifier, we have to recursively compare the type of sigma 1 and sigma 2. And here, importantly, we need to check that this type variable A is fresh, and it does not appear in the free variables of sigma 1. And this check is called the Skolem escape check, which is also crucial to the soundness of higher rank polymorphism. And when the polymorphic quantifier is on the left, then we have the freedom to choose type of tau to instantiate for this free type variable A in sigma 1. And we can instantiate this type to a monomorphic type tau, right? That is in the non-level-based system. In the level-based system, again, in the subtyping relation, we associate the relation with the level number n, and the level number basically says that the relation it could use type with levels less than or equal to n. And the corresponding rule for all R and for L are as follows. And in the when the polymorphic type is when the universal quantifier is on the right, we first again subtype type of sigma 1 and sigma 2, and here we again bumps the level number to n+1, and the free type variable A is now at n+1 because it's only usable after we get rid of the universal quantifier. And when the universal quantifier is on the left, when we're comparing for A dot sigma 1 to be less than sigma 2, we are allowed to instantiate this A to a monomorphic type, which is at level at most n, so that it could not refer to the type which is especially a free Skolem type at level n+1. Okay, so our formalism, we provided mechanized meta theory in the rock theorem prover. We have the non-level-based type system, which I just showed you, and we have a level-based type system, which has a level number on that, right? And these two systems are proven to be sound and complete in the rock theorem prover. And the sound and completeness, they relies on key level-based invariants, and the details could be found in the paper. And in the proofs, we reviewed novel level-related properties to prove completeness of this of the level-based system, and such as notions of level matching and compatibility. Okay, and additionally, we have a formalization of the algorithmic type system. And in the algorithmic type system, additionally to the term context, we have an algorithmic type context, which keeps track of the levels of type constructors and the so-called, again, Scolen type variables. And we have unification variables in the typing context, which are alpha hat, and they have a level number on that. And the unification variables, they can be solved to monomorphic types as tau. And here, there is another important invariant that the solutions of the unification variables, they could be at most level n. And the result of the algorithmic type system is that we have proved the algorithmic type system, which is a green set of judgment forms. They are sometimes complete to the declarative systems that we proved sometimes complete in the Rock theorem prover. And this result is also under the important level-based well-formedness conditions. So, so in our paper, we also have done some case studies. We explored the use of levels in the GHC, which is the state-of-the-art Haskell language compiler. And levels, they are, in addition to their generalization and higher rank polymorphism, it is also used for kind polymorphism and type inference for GATTs and etc. And for OCaml type checker, OCaml has some very smart and optimizes use of levels. For example, in OCaml, types, they themselves directly associate a level, while in our formalism, we only associate levels to type variables, and we have to traverse the whole type to compute the level of the type. And as for our implementation in the, for the COCA compiler, we have implemented the level-based type inference for COCA, and we, as a preliminary evaluation result, we evaluated our implementation by generalization, which is a benchmark that emphasizes the generalization process, and the generalization is tested on varying type context sizes so as to stress the performance improvement of the level-based generalization. And as you can see, the trend of the performance improvement, where the blue bars are the level-based COCA and the red bars are the original COCA, which has a traditional context traversal approach to do level-based generalization and Scolen escape checks. Okay, so as a conclusion, we have more in our artifact and our paper. We have mechanized proofs and the COCA implementation. They are in the artifact, which is evaluated as reusable. And we have a complete formalism of blade-based systems and very detailed examples of the declarative and algorithmic system in the paper, and the soundness and completeness results. And also the details of our implementation and of the validation and evaluation of the implementation. And thanks for your attention, and I'm happy to take your questions.
So do we have some questions from the audience? Okay. I have a question. So your algorithmic system, is that also mechanized in the Rock theorem prover?
No.
Can we go back a few slides just to?
Yep.
So my understanding is the soundness and completeness theorems. Do you have a plan to mechanize that, and like what would be challenges that you see to mechanizing your soundness and completeness theorems here?
Right. Thanks for the question. So yeah, currently the result is not mechanized, and we are definitely interested in mechanize this system. And as you may know, the mechanization of type inference is actually a bit hard because you have to deal with the binding and the scope carefully in the theorem prover. But we believe that the integration of levels to the mechanized type inference algorithm does not really bring any fundamental challenge, because I think the level numbers, they are more or less as orthogonal concern to the difficulties of mechanization of type inference, I think.
Thank you. And can we look at your benchmarks really quickly? Could you bring that slide up one more time? How did you choose your benchmarks here?
Right.
From COCA?
So that's a good question. The benchmarks, they were some randomly generated functions, and it's a big top-level function which has some nested little functions inside, and we nest 200 functions in it. And in the top level function here, we adjust the number of parameters so as we can adjust the number, the size of the typing context to control that. And yeah, and we run the benchmark like for 10 times and take the average.
Okay, thank you. Oh, we have a question, please.
Nick Swami, Microsoft. I'm just wondering, we had this talk yesterday from Dan about another kind of type inference, and he was talking about static overloading, and I'm wondering if your level-based system would be able to handle this kind of thing also?
Right. So, right, I think, yeah, so I think DOM system more address the problem of the declarative system, especially when there is absence of principal types. In the system under prefix, we can properly reject those programs without principal types. And I think the integration of levels, they should be mostly, especially static overloading, they should be mostly orthogonal consonants, I guess. But if we integrate some other features like the trickier examples of GADTs and even first-class polymorphism, it could be trickier, I think.
Let's thank our speaker again. All right, almost. Does anyone in the audience have a joke?
Oh, okay.
No?
No.
No, oh, no, we're ready, okay.
Not so good,
No.
sorry. All right.
Beautiful.
So I'm starting my presentation. Thank you for introduction. I'm Hiromi Ogawa from University of Tsukuba, and today I'm going to present Rust, a proxy-based refinement type system for Rust. So Rust is a popular general-purpose programming language adapted across a wide range of software development fields, and it allows low-level operations for high-performance applications and system programming while ensuring memory safety through its unique type system. And in normal Rust, what we call safe Rust here, Rust type system ensures memory safety for us, and by constraining pointer manipulation operations. And that constraint provides a good properties for higher level static verification. On the other hand, in code fragments that explicitly marked as unsafe, users are responsible for ensuring memory safety. So low pointer operations are permitted, and that makes such verification harder. Our work focuses on safe Rust to leverage Rust guarantees for higher level static verification. Key property of safe Rust is aliasing extra mutability. In Rust, there are two kinds of pointers. One is immutable, and another is mutable. So when the pointer is immutable, there may be multiple areas of it. However, when the pointer is mutable, and in safe Rust, that pointer must be the only one accessible areas. So I'll illustrate that using the example. And this blue circle shows that the variable is accessible. So in this first line, a new memory location is allocated by box new call, whose content is integer 2, and it is bound to variable x. In the next line, we make a new mutable reference to the content of x, and it is bound to a variable m. Here, you can see that permission is temporarily transferred from x to m. This is what we call mutable barrel. And since m has the permission now, we can make an assignment to m updating its value, while touching x is disallowed here. Then, after the usage of mutable reference m ends, the permission automatically returns back to x, and that allows us to assert on the value of x. So this is the intuition of aliasing mutability rule. And because of that, if we try to update m after the last line, it is not allowed and rejected by compiler because x is also accessible here. So this property is higher level static verification of functional correctness in Rust because it reduces the scope of pointer aliasing. And various static verification tools have been proposed leveraging this property. And this table is a summarization of our evaluation of other tools. And automated dimension means the tool can infer inductive invariance automatically. And modular means it can divide verification into smaller tractable parts. And precise means it can track state change via pointers precisely. And there are also dimensions for some language features. So as you can see from this table, now despite their individual strengths, now the tool provides a balanced solution that addresses all these dimensions. To fill this gap, we present as Rust, a new static verification tool for Rust that is designed to be a comprehensive solution in terms of all these dimensions. So for this design goal, we integrated refinement types, flow sensitivity, prophecies, and CHC solving, each of which I'll explain later. For the 4 dimensions I described earlier, refinement types contribute to modularity and language features. Flow sensitivity and prophecies are essential for the high precision. And CHC solving contributes to powerful automation. So let's take a look at individual ingredients. First is refinement types, which is types qualified with predicates. And as you can see from this example, this is a dependent function type. You can specify a pre and post condition of the function type, enabling verification of functional correctness. And so refinement types contribute to supporting various language features and modular verification. Also, automatic inference of refinement types are studied. So functional correctness verification via refinement types can be automated. However, modularity and automation are in trade-off relationship. So you can see from the left example, this is a full automated for program verification that only takes input program at once and verifies it at once. And it doesn't take user annotation. So it can be problematic and often result in timeout if the input program is large. However, on the right, you can see a modular but semi-automated verification. So it requires users to give an annotation on every single function in the program. So this makes verification problems smaller and tractable, but that simply writing annotation is tedious for users. So actually, Rust is not only modular, but takes a good part of both approaches. Because refinement types works as a verification boundaries, making verification modular, but also refinement types can be omitted if user wishes, and let Rust can infer these types automatically for you. So refinement types works as a flexible boundary of verification, striking a balance between automation and modularity. And also, Rust accommodates higher order functions and algebraic data types thanks to refinement types. So both features are essential for practical Rust programming. What about mutation? The mutation is also essential feature in Rust programming, and we want to track the effect of mutation precisely in our type system. So let's see how that works in refinement type system. This is the refinement type of variable x, and that essentially says that the content of x equals to an integer 2. And in next line, we want to update the value of x. But this does not type check naively, because simply variable 1 is not compatible with value 2. So what about giving a more relaxed type like this? So star x equals 2 or star x equals 1. So this can indeed type check this assignment, but this cannot discharge the assertion on the last line because this type system doesn't know the exact value x has even after this assignment. So this is imprecise and also not what we want. Actually, we have to update the type like this after the assignment, and this makes our type system flow sensitive because the type changes over the course of typing, And also this kind of type overwriting is called strong update. But library supporting strong updates can easily lead to unsoundness. So let's say example, on the right you can see refinement types. And in the next line, we create a new variable v that has a value of the current x. And then we make a strong update. So here, as we discussed before, the type of x destructively update to be a box of 1. But this confuses the type system. On the last line, we have an assertion assertion about the value of v, but this fails in runtime. But this type system concludes incorrectly that this assertion holds because of this strong updates. So this is a challenge. And we have a solution in /type system, and we separated the typing context. We have 2 typing contexts in our type system. First is place context, what we denote as delta, that binds program variables. And second is typing context, which we denote as gamma, that binds immutable snapshot of program variables in delta. So it's important to note that program variables are not bound in gamma, so first we have to bind program variables in delta. So let's see that in example. First, we have on the pointer and bind that to variable x, and it is bound in delta. Here, the logical representation of the value is bound in delta, and its inner snapshot, the immutable part of that representation, is bound in gamma, along with its refinement. So it says that the x prime is the freshly allocated variable, and its value is 2. In the next line, we create a new variable v, and as we know, the current value of x equals to x prime, we just bind x prime to v. And then we make a strong update. But that happens on delta, not in gamma. So here, content of x is replaced with x double prime. It is another freshly allocated variable, but the refinements in gamma does not change during the course of typing. So that preserves the logical meaning of v during typing, and this system can successfully reject the assertion on the last line. But we have another challenge. So this is mutable references. Mutable references are also essential for practical Rust programming. But we need to propagate change made through references to their owner to support mutable references. In this example, we have a mutable reference m that points to x, and in some way, this type system can give a type m that equals to 2. And in this next line, we call decrement function that decrements its argument by 1. And so suppose that this system can, in some way, give a type m to be decremented 1, time equal 1. But so this can successfully discharge this assertion about m, but we also have an assertion on x. And according to the aliasing between m and x, the last line, the assertion will fail in runtime. But since we didn't change the type of x, this system incorrectly concludes that this holds. So this is unsound, and we have to deal with this. So this is actually very challenging because we didn't even have any occurrence of x between this mutation and this read. So we have to propagate the value this way, backward way. So this is where the prophecy comes into our type system. Prophecies are no way to aid reasoning about future states, and several large verification tools have adapted prophecies for their own verification, and similarly start incorporated prophecies to handle mutable references. Still, we need to adapt that idea because Rust is type system-based formalization, while the prior work, Rust Home, is not. So this is the representation of mutable references in our system. So this is just a pair, and the first one is the current value of the owner, and the second one is called prophecy, and it is the future value of the owner, and also it is the final value of the reference. And we denote this first one using a star operator, and the second one using circle operator. So this example is a decrement function that decrements its argument, and that effect is expressed on the return type of this function. So here, this return type asserts that the prophecy of m equals to the value of m on the entry of call minus 1. So this is the effect of decrement function. All right. So let's see how this works in the typing environment. So this, as always, we bind a new on pointer in respective environment, and then we create a new mutable reference. And here, our type system freshly allocated a new prophecy variable, which is named L in this example, and use that to link owners and references. Owner is X here, and reference is M here. Here, so we replace the current value of inner value of X with L, and we use L as a prophecy of M. So this means that if when we use X after this statement, according to last borrowing rules, the reference M must have already been expired. So the value after that happens, the value of X after that event must be the last value of M just before the expiration. And that's exactly what prophecy means here. So let's see how this works. In the next line, we call decrement function on M, and we get new assumption from its return type. And by substituting its parameter using parameter with its argument logical representation, we get this term and can be reduced to this term. All right? And then our system can successfully discharge the assertion on the current value of X thanks to prophecies. So because star X, which is the current value of X, equals to L, and L equals to X prime minus 1, we know this assertion certainly holds. Okay. So this is the overview of our type system, and we prove the soundness of our type system under the property named well-boundedness, which is the formalization of aliasing extra mutability property. And the important thing is that our formalization does not depend on any specific implementation of barrel checker. This design accommodates future version of the last barrel checker. And we have to talk about automation. So we adapted a non-CC-based refinement type inference method that works in 3 steps. First, it generates a template of unknown refinement type using a predicate variable, and then generates a constraint that the predicate variable must satisfy in the form of constraint home clauses or CHCs. And finally, give the constraint to the solver and let the solver solve them. And we get this kind of complex refinement type, and we don't have to write this kind of complex type, but Thrust infers that automatically for you. And also, Thrust really utilizes CHC solving to automate reasoning about pointers, loops, or recursive function at once, thanks to our use of prophecy variables. So next is evaluation. So we conducted 2 experiments using 2 benchmark sets to check whether Thrust has achieved its design goal and to compare Thrust with other competing CHC-based Rust verifier. For the first benchmark, we created a new benchmark set to compare a broader range of Rust verifiers. And this is a summary of results. And in paper, we have 32 results, and this is the extraction. And in summary, this shows that Thrust has achieved its design goal. So we have some example of the benchmark cases, and this shows the precision of Thrust over the existing tool. And this shows in this example, Thrust performed better than the existing Rust verification tool. And also, we conduct a performance comparison against the last one, the prior work, and using a last one benchmark set. And as you can see from this scatter plot, verification with Thrust was completed in a comparable time with last one. But there are also slower cases, but we analyze that in paper, and this is our future work to address these slower cases. So that's all my presentation, and I'm happy to take questions. Thank you.
Okay. We can take questions from the audience.
Hi. Oh, sorry.
We're going to start up here first.
Okay, thank you. Thank you for the talk. So I was curious about your prophecies. What's their connection with like post conditions in general?
Thank you for your question. Prophecy is a post condition is in general shows that prophecy is for like a post condition for mutable references. So prophecy shows the future state of mutable references, and it can be used to specify post condition of its parameter. Is it make sense?
Yeah, we can also talk later, but thank you.
Yeah, thank you.
Go ahead.
Hi, Derek Dreyer, Max Planck Institute. Very interesting work. So I have a question about the comparison with the refined Rust, actually. So refined Rust, as you know, as you cited, is also a refinement type system based on prophecies. And the type, when you showed the typing rules, I don't know if you can go back to the slide on where you were showing the typing, presenting the typing rules was a way. Basically, this part. So this felt very similar to how this would be type checked with refined Rust. So I was wondering if you could compare more technically, like what is the technical difference? I mean, I understand the automation is completely different. It's much more automated than refined Rust, but I'm wondering what the technical difference is in the type system itself.
Okay, thank you for the question. So first of all, behind us and Rust differs in design prophecy, design philosophy, but in detailed type system, I can't say much about the technical difference between type system, but one thing I can say is that behind us can handle unsafe code by lowering them to separation logic, but our system is not. We just handle safe Rust, and I think that also contributes to powerful automation. And automation is, as you said, the core difference between behind Rust and Rust. So, yeah. So, but we can discuss that later. And thank you for the question.
Okay, thanks.
Okay, we have time maybe for one more question. Yeah, we could try and get to both of them, but.
Hi, Ralph Young, ETH Zurich. Thanks a lot for the talk. Always nice to see more Rust verification. I was a bit surprised by your mention of stack burrows. So I wondered stack burrows doesn't do anything for nested references, right? It only really cares about the top level reference. So it seems like not enough to assume stack burrows if you want to actually have a type system where I can nest references arbitrarily. Like what do you do with nested references, and how does that relate to what stack burrows does with nested references? I'm a bit confused there.
So you mean that stack burrow is not enough to say handles nested reference in type system soundly? So yes. Sorry. So let's discuss that later. But
yeah, let's follow up. There's a lot of interest,
really
but it's lunchtime,
question.
so let's thank our speaker one more time.
Hello. Okay, let's get started, everyone. Welcome to the final session of PLDI 2026. You're in the static analysis and verification session. We have a set of 4 very interesting papers for the session, and we're going to start with our speaker, Gabriel Ebner. He's going to be telling us about PulseCore, a new system for verifying concurrent higher order programs.
Oh, thank you. So at Microsoft Research, there's a bit of an echo, sorry. We believe that proof-oriented programming with intrinsic proof works. I mean, like, to show this, over the years, we have developed about 1 million lines of code of verified star code that is deployed in various industrial applications. We have a cryptography that is deployed in Linux, in Python, in Firefox. We have verified parsers that are deployed in Windows, in Azure. Might be that like most people in this room have something running right now that is developed at Microsoft, written in F-star, and deployed in production. But we are running into limitations, and we want to expand beyond our successes. There are limitations to how we've been doing things. So we were using a system called Lodestar, which has a direct encoding of heaps, where you need to actually reason about heaps directly. And it also didn't have any concurrency, and its foundational model was more of a axiomatized effects in F-star style. And so if you look at the landscape of program verification these days, there is Iris, Iris, and Iris, and Iris is really amazing. But usually when people use Iris, they do a deep embedding of a proof of a program in Coq, and then do extrinsic proofs about that. But we want something that is intrinsic, that is in F-star, that where you interleave the proof with the program. And we also wanted to integrate with all the native effects in F-star. F-star has effects for ghost state, it has effects for divergence, and we want this to interoperate nicely. And to solve this problem, we have developed Pulse, a new separation logic that is written in F-star, and that does a lot of what Iris does, just in a smaller footprint, and integrated in F-star. So in particular, our foundation does not require any categorical machinery. There is no COFIs, no cameras, no ultramatic spaces, just what you can do in F-star. And roughly, the architecture looks pretty straightforward. So we're building on top of F-star, and not even full F-star, just a very basic total subset of F-star. There is none of the extremely sophisticated effects that we have available. So this is a foundation. The part of F-star we use is something you could do in any other proof assistant. You can do it in Lean, you can do it in Coq, you can probably even do it in Actor. And on top of that, we built a development of heaps, of atomic actions that operate on heaps, and then lift it into divergent computations. And on top of that, we have a new domain-specific language, Pulse. And using this domain-specific language, we have developed about 100,000 lines of code to evaluate this system. And yeah, the existing F-star system is very useful because it already allows us to do the whole code extraction pipeline. We can extract to C, we can extract to Safe Rust, we can extract to OCaml, and that's what we actually make use of. So let's get started with some examples from the Pulse DSL. So if you recall the slide, the title slide, there was a word impredicative on it. And I'd like to just get enough separation logic so that you can understand that single word. OK, so let me show you very quickly how Pulse looks like. So the key message here is Pulse is F-star plus mutability with separation logic-based ownership reasoning, a bit like linear types. And so if you have any dependently typed function that is already in pure F-star, you can directly use it from your Pulse program, even if it was not at all defined using Pulse. This is just the standard plus function in F-star. So you can use that in F-star with the dependent type. And then on top of this pure basis of F-star, we add mutable state. And for that, we get extra pre- and post conditions using separation logic. So these separation logic propositions, they encode resource ownership. So if you have a reference, you have a precondition that you own the reference and that the reference points to the value VR in this case. And then you just write your program with function calls that modify those resources that you have. And if you, for example, assign to your variable, then suddenly your resource changes to reflect the change in value. Now, in F star, in Pulse, we encode both the pre and post conditions, as well as what kind of function it is in the type. So on the previous slide, we saw like a regular function with side effect that is actually executed, but we also have ghost functions. Those correspond a bit, if you know Iris, to few shifts. And syntactically, those just differ by having a ghost keyword. And the story here is that these functions, they are only there for modeling. They are not they are not executed. They are erased. And all the ghost state, now a ghost function, what can it do? It can access a special part of the heap, that is the ghost heap, which only contains references that are not there at runtime, that are just there, for example, for bookkeeping when you want to verify concurrent programs. And all the ghost data we have in Pulse can be allocated and used just like regular references. You can allocate them, you can write to them, you can free them. And you can do this locally. You don't need to do any global setup whatsoever. And obviously, this is also defined for PCMs. So if you want to have some kind of complicated ghost state, monotonic state, you can define this in just the usual way. We even have like refined PCMs where you can give a subset of possible values for the memory representation. Another special kind of Pulse functions are atomic functions. So we don't extrinsically prove that functions are atomic. Instead, we have types that say, hey, this is an atomic function. And then the type checker verifies that essentially these functions only execute at most one atomic machine operation. And they look syntactically just like ghost functions, just like regular functions. And the type checker also allows you to run ghost functions inside an atomic function or after an atomic function, it is still atomic. Under the hood, this is all implemented using kind of monadic types. So there's a monad for atomic functions with a bind operation, and this surface syntax desugars into the monadic stuff. OK, now that we have these basic ingredients, let's get to like the core of the paper, invariants. OK, this is maybe a somewhat confusing topic, because the name kind of suggests that, hey, maybe this is like a loop invariant, but it's not. Maybe you think, OK, it's like invariant on a binary tree, also not. So the name invariant, I'm not sure who exactly introduced it, but it refers to something that is true after every atomic step of your execution. And since you're in separation logic, it's not just true, but you also get ownership over it. So like the slogan that I want you to remember is that it is a named resource that you can temporarily borrow during one atomic operation, and then you have to give back. So it has nothing to do with loop invariants. It is an ownership construct. And it allows you to transfer resources between threads. And it's used to implement mutices, condition variables, any kind of concurrent data structure that you can think of. To give you a small example, let's look at how the invariant for a spin lock would look like. So here we've got this example. There's a predicate which is called if true then owns, and it is parameterized by a reference to a Boolean and a separation logic resource protected. So like that's just the SL prop, the heap predicate, and it's defined as there exists a value for this reference, and we own the reference, and if that value is true, then we also store the protected resource. And if we put this into an invariant, we then get two state transitions. If we have if the reference points to true, then the invariant also contains the protected resource. And if we acquire the spin lock, then the reference switches to false. And during this atomic switch, we can take out the protected, and afterwards, the invariant only owns the reference. So this is kind of like how these invariants look like. And the key thing that now I guess everybody has already discovered is that these invariants should be impredicative. And impredicative means that invariants can own invariants, that you can have an invariant inside an invariant. And previously, we saw that what this means is that, for example, the thing that is inside the lock can be, again, for example, another lock. So this captures the, so imperative means that you can have locks that protect locks. You can have task pools that store tasks that refer to the task pool itself. You can also like have concurrent linked lists where each element in the linked list protects the ones that come afterwards. Okay, so it's really important that you can have this circularity in invariance. And generally speaking, with invariance, there are like two intricacies. One is that we need to make sure that invariance cannot be opened twice. I mean, usually you have some kind of invariant mask that tells you what you've already opened. And the other one is that this impredicativity requires some guards against unsoundness. If you put this in like naively, you get unsoundness in your system. And generally, you resolve this by adding step indexing in the later modality. We do this just like in Iris. And syntactically, the API for this looks very straightforward. In Pulse, we get a ghost function that turns any resource P into an invariant. We can duplicate it, this inf_i predicate, to send it to other threads. And if you want to use it, there is a nice surface structured control flow that allows you to open an invariant. And for the duration of this one atomic operation, you get the content of the invariant guarded by the so-called later modality. And this later modality and the associated later credits are an awesome invention from Iris, just from like, what, 3 years ago now. You can introduce this later modality using the later intro function. This is always possible, but to eliminate it, you require later credits. And the key trick here is that those later credits can be obtained outside of the atomic block. And since we're doing this intrinsic proof style, we can actually instrument the program so that you can obtain those credits at any point. And like you don't see any kind of update modalities here, mainly because we can like stuff those modalities into this later credit by function here. Okay, now this was a bit about how the Pulse DSL looks like. And now let's go to the implementation, about the theoretical foundations of it. So previously we were up there at the Pulse DSL, and let's now dive a bit into Pulse core. So in the Pulse heap type has like 3 main components. One is the concrete heap, which models pretty much the physical memory. It's a map from physical addresses to stuff that is in memory. There's another field in that structure, which is the ghost heap. That one is erased. It does not appear at runtime. And then there is a higher order heap, which contains the invariants. It contains stored predicates, as well as the number of credits that are saved. And we found that those primitives are already enough to define most higher order state that you encounter in practice. I mean, there's some stuff that you cannot easily define using this. Like you cannot easily store, for example, heap predicate transformers. I mean, you can still encode them, but you cannot store them directly. Obviously, the big challenge here is how to define such a heap, because again, the heap contains invariants, which contain heaps. And so generally speaking, this requires the solution of some kind of domain equation. Because the naive solution to this is, if you're just focusing here on the part where we store invariants, then you get that like the heap needs to contain a map from addresses to heap predicates, and that is unsound for cardinality reasons. So now Iris solves this domain equation by defining a functor, an endo-bifunctor on a category of cofees, and then applies some sophisticated categorical machinery to construct a fixed point for this. But I'm very grateful for some anonymous reviewers of our previous version of this paper to point us to a much more simple and more elementary solution to this problem called indirection theory by Hober and Apple in 2010. And this, interesting enough, is the formal foundation of VST, of the VST verifier. And from what I understand, like they moved away from VST to Iris because it didn't do invariants or any of these other cool modern features. But we managed to extend indirection theory with invariants and later credits, and to get a nice modern separation logic with impredicative invariants. And like what interaction theory gives you is a solution to this domain equation which introduces the levels by itself. So given so here, if you look at the second one, you get that the heap is kind of equivalent to the natural number, like a level, product, the address to heap predicate. And for any functor which turns a heap predicate into a heap, interaction theory gives you this kind of level stratified approximation. It's an approximation because the right to left map zero truncates the predicates to the current level. And this is really simple. It's like just 70 lines of F star, this core domain equation solver. Like maybe this diagram explains this a bit more. So like you get top level predicates that range over any heap. And then like the heap n contains predicates that only range over heaps that are strictly smaller. And the rest is just zero extended. And you can define this using just a well-founded recursion on the type in your favorite dependent type theory. Just define heap n is something something of heap m. Right. Yeah, and on top of that, we add these intrinsically typed actions. And those are, we are doing a shallow embedding. So these are really just pure F star functions that take one heap and give you back the output heap as well as the return value with some obvious side conditions that the input heap satisfies the precondition, an arbitrary frame, and the invariance. And there's, the way we encode these later credits is simply by requiring that the level of the heap minus the stored credits is greater than 0 and decreases by at most 1. It's super straightforward. And ghost functions are just add one more extra condition, namely that they preserve the concrete heap. And this has then the effect that you can actually like turn an erased ghost action into a ghost action. So you can just store them as proofs. And on top of these actions, we now add a definitional interpreter to model divergence states. So we have a tree of actions, an infinite tree, and we write a field interpreter that gives semantic to this tree. And this definitional interpreter is correct by typing, and it's just a way to model the semantics. The extraction is separate. OK, to conclude, the paper has 3 case studies. We have a task pool, a barriers, and a verified measured boot protocol. And there's lots of other stuff in Pulse. We got a core library, we got verified parsers, we got GPU kernels. And from here on, we're like looking to extend Pulse both on the theoretical side, doing prophecies, total correctness, and doing lots of implementation goodies, the new C front end, and just making it nicer to use. Thank you.
We have time for a couple of questions.
Hi, Ralph Jung, ETH Zurich. Thanks for the talk. Very nice to see Iris and F star. I was wondering if you could say a bit about what you did on the resource side, like for the concrete PCMs that you own. Is it PCMs? Is it more like Iris's resource algebras? Are those the same because you just don't have a core? Like what are you doing on that front?
To be honest, I'm not fully clear on what resource algebras are in Iris. So in the heap impulse is really just a map from addresses to a type, a PCM on that type, and a value of that PCM.
Okay, and then like for the PCMs, do you have like some standard PCMs to keep reusing, or? Like?
Oh yes. So like we've probably already seen like the most straightforward one, the ones that just allows you to write one value and then like with fractional permissions. You can use you can write your own PCMs, and then we have a library for various other PCMs like fancy constructions, anchored pre-orders,
Okay. Yeah, resource algebras are kind of a fun way to build more PCMs than if you just build them from smaller PCMs. Anyway, happy to talk later.
Oh yeah. I mean, like we can also do products. Yeah.
Yeah, sums work better. And anyway, we can talk later.
Okay. Yeah. Thanks.
We can do one more quick question, quickish, hopefully. And yeah, the next speaker can get set up, please.
Yeah. Hi, Derek Dreyer. So I'm
Okay, let's thank the speaker again. Okay, our next speaker is Longfei Chu. He's going to be telling us about a new technique for verifying blockchain protocols.
Okay, hello everyone, I'm Longfei Chu, and I will talk about Lido DAG, which is our approach for formally verifying safety and liveness of DAG-based consensus protocols. So for the introduction, let's begin from the concept of consensus protocols. Well, in several blockchains, you have several clients submitting requests to a central distributed ledger. And the goal of consensus protocol is to make all the computing nodes in this system agree on a total order of these client requests. So for example, you have 3 replicas here, and they can all receive requests from clients. And the system can add these requests to the consensus log at an arbitrary order, but every replica must receive these requests in the same order. Now, given that consensus protocols play a central role in many distributed systems, including blockchains, you can easily think that there's a long line of work trying to optimize all different aspects of consensus protocols. So in 2019, the state-of-the-art of consensus protocol is probably hot stuff, which is still a Paxos-like leader-based consensus. But then in 2021, Denizis et al. Introduced the Narwhal protocol, which introduced the idea of having a DAG-based mempool in the consensus protocol. And subsequently, there is a very long line of work trying to optimize all different the throughput and latency properties of Narwhal. And furthermore, there's a general trend in the blockchain community to move away from leader-based consensus protocols and into these so-called DAG-based protocols. And this leads us to the central topic of this talk, which is DAG-based consensus. Here, DAG stands for Directed Acyclic Graph. These protocols all revolve around the following idea. We make the processes collaborate to build a DAG mempool of these data blocks or request blocks. And then we make these individual processes run an algorithm to interpret the locally observed DAG to get the consensus log. That's quite different from the Paxos-like leader-based consensus protocols. The advantage of these protocols is that you can get much better throughput than Paxos-like protocols. But with these additional components of mempool, you can imagine they have much more complex implementations and also much more complex security proofs. And like anything that gets too complex, inevitably we will have a lot of subtle bugs creeping into these protocols. So there has been multiple works which claim they found issues in previous proposed protocols, like this paper which says there is an issue with mysticity liveness proof, and this paper which says there are several robustness issues across DAG protocol implementations. Naturally, we want to ask, how can we give strong security guarantees to these protocols? Well, the only way to give absolute correctness guarantee to these protocols is to formally model them in a specification language and also construct mechanized proofs for these properties. But although you probably haven't heard of any of these protocols before this talk, you probably have heard of Paxos. And Paxos only relies on timers, and they don't have Byzantine faults. And it's already difficult to verify Paxos. Now, DAG-based protocols use a lot more different components, and they have different states, such as timers, reliable broadcast, and other optimizations. So it's probably not a good idea to directly try to model every piece of detail of these protocols. So we ask, how can we abstractly specify the formal correctness criteria for these new protocols? How can we efficiently verify these protocols for the new of these properties for the new protocols? And how to make these proofs more reusable? Well, we claim we can handle all three challenges by introducing an abstract model for DAG-based consensus, and we can easily connect the different protocols in the literature to our model by refinement proofs. So for the rest of the talk, I will first give a bit more background about our work, and then we dive into the details of these protocols and how we formally verify them. So DAG-based protocols belong to a broader class of Byzantine fault tolerance protocols. So in any distributed system, we must prepare for a subset of the components to fail. And by Byzantine fault, we mean after a computing node fails, we assume it is corrupted and can inject any message into the system. And remember that the network infrastructure can also fail. And so we also need to assume the communication model. In this work, we mostly focus on the partially synchronous model, which says there is an unknown time point called the GST. And before GST, the network can arbitrarily drop or delay message delivery. But after GST, the network must deliver all messages within a known time bound. Let's call it delta. Now, there's a large number of consensus algorithms proposed for the partially synchronous Byzantine model, but most of them fall under what we call leader-based consensus. The basic idea is that at any given time, there is a single elected leader, and only this leader is proposing blocks to be committed by the other nodes. So you can see on the left, there is only this node 2 sending out those requests. But when this leader fails, we trigger a timeout or a view change protocol to make them switch the leader. Now, these protocols are easy to implement, and they are very well understood, but there's an obvious problem, which is that the leader is a bottleneck of network throughput. So people ask, can we make all processes make some progress even when they are not leaders? And the DAG-based protocol is essentially the current response to this question. The idea is that we have this DAG-based mempool. Each vertex on this graph represents a data block, and every process can add blocks to the mempool. And now from this figure, you can immediately see one thing, which is that this DAG graph only provides a partial order over these blocks. So it doesn't really give you a total order over the requests. And so we need an additional mechanism to reach consensus on the order. Now, exactly how this is achieved is now an active research area with many proposed solutions. We already saw in previous slides some of the major steps in this area, but there's many, many more protocols that are very recently proposed, and they are some of them are already deployed into existing blockchains. Now, why do we claim that we can use abstract models to simplify verification of these protocols? Well, abstract models give you a simple way to specify the expected behavior of a system. The idea is that you don't introduce all the network level details like timers and reliable broadcast all at once. You first specify a simple transition system which captures the core logic of these protocols. And then you gradually add in the network level details by refinement proof. And it turns out both safety and liveness can be proved by refinement. We will talk about how to do this later. In our last year's work, we proposed the Lido model, which is an abstract model for leader-based consensus, and we applied it to several state-of-the-art consensus protocols. For example, this is how we proved the Jotian protocol by layered refinement. At the top level, we have this abstract model, and then in the second layer, we add in the proposer state. Third layer, we add in those voter and the timer state, and finally, we reach the network state. So can we apply similar techniques to DAG-based consensus? And our answer is yes, which leads us to the core contribution of this work, which is the Lido DAG model. Now, before I introduce the technical details, it's useful to first have a rough idea of how these DAG-based protocols work. They usually work through 3 major steps. The first step is to designate a subset of the DAG vertices as so-called anchors or leader vertices, and how this is designated is protocol dependent. For example, this is a figure for the Bolshak protocol, which is a simple DAG-based protocol. And you can see that in every second round, you have one of the vertices marked red. And this is what we call the anchor vertices. It's essentially the anchor created by the leader of the odd number round. At any given moment, the individual processes observe a subgraph of the global DAG, and then the protocol defines an algorithm to interpret the locally observed DAG to get a list of the so-called committed anchors. And this is a total ordered list. And then we expand each anchor into the list of all directly or indirectly referenced blocks. So this means if your block is referenced by one of the anchors and this anchor gets committed, then your block also gets committed. And this is why with each commit of the protocol, we can commit a large number of data requests. Now, our key observation of this work is that these DAG-based protocols, although they seem quite different from leader-based consensus, we can actually interpret them as simulating leader-based consensus. Now, notice that in the previous figure I showed, there is only one anchor. Periodically, you have a single anchor in the graph. This actually, we can make an analogy between these anchors and leader proposals. Now, references to these anchors would correspond to commit votes. And recall that in Paxos-like protocols, you need a quorum of commit votes to commit a certain request. And so if we continue this analogy, then a quorum of references would correspond to a commit certificate. So can we formally capture this simulation? Well, we claim it's very easy to do so using our Lido model. So here's a review of the Lido model, which we proposed last year. It's an abstract transition system whose state consists of 2 major components. The first one is a cache tree representation of the consensus log. The second one is what we call the abstract pacemaker. The idea of the cache tree is that in leader-based consensus protocols, we can divide the system execution into views. And in each view, we postulate that the system has to progress through 3 abstract events, which we call pull, invoke, and push. Intuitively, what you do in each view is to append a single entry to the consensus log. But before you can append the entry, you have to first determine where to append your entry. And that's the pull step. And in invoke step, you actually append your entry. And in push step, you attempt to commit your entry, which might succeed or fail. And the cache tree is a graphical representation of the result of these steps. Here's an example. So you can see here that since the C cache represents a successful commit, and we don't have C cache in the second view too, shown on the top right here, it's perfectly fine for the third view not to follow the second view and simply append from the method of the first view. You don't have to understand this because later I'll give a step-by-step demonstration for DAG-based protocol. Now, the cache tree representation is useful for proving safety of these protocols, but it's not sufficient to prove liveness, because to prove liveness, you have to show that after a leader sends out a request, the voters will vote for it before timeout. And this before timeout part is crucial. So we introduced the abstract pacemaker, which summarizes the state of local timers. So we know that when exactly these timers will time out. Now, the idea of Lido DAG model is as follows. In the DAG-based protocols, we still have this view succession, but these are logical views. These protocols don't explicitly introduce the idea of views, so they are logical. And in each logical view, there's still a pre-designated leader. And what it does is, instead of proposing a single block, it chooses one of the vertices in the global DAG as the new anchor to be committed. And so instead of having M caches or your invoke step proposing single block, you propose references to the DAG graph. So here's how the Bolshak protocol can be interpreted under this framework. Well, in the first round, you have this anchor A1. Naturally, it's attached to root because there's nothing before it. In the second round, this is, we try to commit the A1 anchor, but it's not successful. You can see there's only one reference to it, and we need a quorum, which is 2 references. So in the second round, the second logical view, which is round 3, we have this anchor A2. Now, A2 doesn't reference A1, so A2 is also attached directly to root. In A3, we finally have an anchor that's committed. You can see that there are 2 references to it, which forms a quorum, and we represent it by a C cache over here. So if from this figure, we can see that the committed leader entry should be A2 and A3. And that's, in fact, exactly how the network level specification of Bolshak works. We also prove liveness of these protocols. It turns out that we can decompose liveness of them into the following safety conditions. First, of course, you have to periodically create new vertices, and then you have to make the leader vertices reference these vertices. And finally, we need to get them eventually committed. So we did several implementations of Lido DAG. Besides Bolshak, we also implemented Narble, which uses an external BFT to order these vertices. We also did Selfish, and in fact, we did 2 versions of it. The second version optimizes the first one by removing 1 extra delta during failover. Our specifications are completely executable. We extracted them to OCaml. And here's the total proof effort. You can see it's a very lightweight way to verify these protocols. So what's the takeaway message of our work? Well, we showed that DAG-based consensus protocols can be interpreted as simulating leader-based consensus. And although it's a folklore that there's a strong analogy between these 2 kinds of protocols, we are the first to formally show that this simulation can be modeled as a refinement relation. And it turns out it's very easy to verify these protocols by proving this refinement. And that concludes my talk. For more technical details, please check out our technical report and artifacts. That's all. Thank you.
Any questions from the audience? Okay, I have a question. So within this framework of yours, can you reason about relative efficiency or optimality of these different protocols? I mean, presumably they're developing them because they care about making them as efficient as possible.
Yeah, so to prove liveness, of course, what we do at a network, what we do is we look at how the system state progresses through these each delta. So we say if the system at GST satisfies a certain condition, then at GST plus delta, you have to satisfy some additional conditions. So you can prove, say, since the protocol claims say we have a commit latency, say it's optimal 3 delta or something, then you can say at GST plus delta, if a leader proposes something at GST plus 4 delta, you will see it committed. And so you can verify all those latency claims in these protocols.
One other quick question, and next speaker can set up.
Thank you for the talk. So could you explain the following thing? So one of the traditional ways to, let's say, prove a safety of consensus is to say, well, my desired property is an agreement, or like some property of this DAG, and then come up with an inductive invariant.
Actually prove this. First, you have to specify your extraction algorithm at the network level, right? And then all your proofs are also tied to your network level specification. And for these protocols, these algorithms are quite complex. You can see it's a two-stage process. We first order all those anchors, and the second stage, we expand all those anchors, right? And it's often not convenient to formally reason about this at network level.
Have you tried the alternative way?
Okay, I think at this point, actually, we should take the discussion offline, sorry, to keep the session on track.
Yeah, we can talk offline about
so, yeah, thank you very much.
You.
Let's thank the speaker again.
Yeah.
Okay, our next speaker is Michael Schwartz, and we're going to be hearing about new techniques to do more precise static analysis of global variables.
Thank you for the introduction. So I want to start off by mentioning that this is joint work together with Fabian Stemmler, who was a master's student in our lab, and also with Julian Erhard, Sarah Tilscher, and Helmut Seidel. And let's start off very easy. Most of you will be familiar with this. So when we do static analysis, we have to do the option to do something that we call a flow-sensitive analysis. And in such an analysis, we would compute basically one piece of information, say from some abstract domain D#, for each of the program points that we have in our program. Sometimes we find this to be expensive, and then we can alternatively go for something that we call a flow-insensitive analysis, and then you would just compute one global piece of information that needs to hold throughout the entire program. However, this is not the only thing. There's also some middle ground between those two things, namely something that we have dubbed mixed flow sensitivity. And the idea is that you are flow sensitive for some information and flow insensitive for another class of information. And then one could say that for the flow sensitive information is associated with something that one calls the locals, and the flow insensitive information is associated with some set of things that one calls the globals. Now there's many instances of this. One of the instances that people might be familiar with is, for example, when you do global store widening, but you don't do it to all variables, but just some of them. Another instance that people might know is that something like this can be helpful when you're doing an efficient yet precise pointer analysis. It also arises when you're sort of analyzing unusual control flow. And it also arises when you want to have a way of expressing different types of having context in your analysis, and you want to have a very flexible framework for it, then it can also be helpful. And perhaps the most common instance of this mixed flow sensitivity is when you do a thread modular analysis of the values of multi-threaded programs. And this is also where we'll be drawing the example from here. So when you do this, then typically you would say that your flow sensitive information is per program point. So your set L would be the program points, and your flow insensitive information you would organize by program global variable, and so your set G would be the global variables of the program. And then one simple idea is that we would flow insensitively accumulate all of the possible values that these global variables can have. Now, if you have powerful abstract domains that have infinite ascending chains, then you have a problem here, because you cannot just accumulate all of the possible values that you might see, or their abstractions, because it might not terminate. So you might need to use something that is called a widening to ensure that this entire thing terminates. So let's take a look at an example. So here we have a relatively simple multi-threaded program. It has two threads. One of them is always increasing I if it's less than 10, and the other one always decreases I if it's greater than minus 10. A variable A is the one that's being modified. So here we would expect that at the end, an invariant for this A could be that it's between minus 10 and 10. So let's take a look at what an analysis might find. You would start analyzing somewhere locally, and then you would find the first contribution or first possible value of A. And if you're doing an interval abstraction, then you would abstract this value 0 here with this interval from 0 to 0. So you would record this contribution, and then you would continue your analysis, and then you read this value of A into your local I. You check the guard holds, and then here you cause another contribution to this global variable I. In this case, this would be the interval 1, 1 that you contribute. And now we said to ensure termination, we are always applying widening here. So we immediately get an interval that goes from 0 to infinity. Now, of course, this value of A has changed, so we need to evaluate this loop one more time. But here, nothing more happens. The value is already subsumed. So at some point, we move on to the other thread. In the other thread, we also read this value of A. We check the guard, so there are values that pass this guard, and then we subtract 1, and this is our new contribution to A. So we find that the contribution to A is in the interval from -1 to infinity. We combine this by widening again, and then we have the top interval, which we have arrived at. So it's nice, our analysis terminated, but also it is actually not what we hope to find out. So actually it turns out that widening at these globals can actually lead to a drastic precision loss at the globals. Now, of course, the problem with widening is not new, so people have proposed solutions. And actually, it was even Couzeau and Couzeau who proposed, okay, if you do widening, then you maybe also need to do narrowing to go back down with the values. So one naive idea might be to say, okay, I just apply narrowing, and I narrow the value of the global with whatever was the last contribution. However, it turns out that you cannot do this. So this is because this value will actually be too small. So what we need is, we need a better idea to apply widening and narrowing for these globals, and the idea later will be to do this per origin, where the contributions come from. Now, initially we said, okay, let's integrate it into our framework, but then we realized that there's a whole zoo of frameworks that somehow support this mixed flow sensitivity. So you can either formulate it as some sort of nested fixed point algorithm. Some people have proposed something that's called a blackboard architecture. Our group has at some point proposed these side effect and constraint systems. So we thought it might be nice to actually be able to have a solution that works for all of them. And to do this, we would like to decouple handling the updates of these globals from the rest of the solving mechanism. And we do this by what we call update rules. Now we need to make some mild assumptions about what the solver does. And our assumption here is that the solver internally has some map rho that maps the globals to the abstract values that you have for them. And then the crucial thing is, we say that the solver itself, it can read this map, but it cannot modify it. The modification of this map, it delegates to something which is this update rule. And this is the signature of such an update rule. And the idea is, whenever the solver has computed a new local value, it will call this update rule, providing for which local the value was computed, so the origin, then it would provide a set of new contributions and the current map rho. And then this update rule would give you back a set of updates that then need to be applied to the solver, to the rho. So if we recall our update rule from earlier, where we just always proposed widening, it might look somewhat like this. So we go through all of the contributions, we see if the contribution is subsumed. If it is, we don't need to do anything. And if it's not subsumed, we perform a widening between the new contribution and the old value that we had in rho, and then return an update for it. Now we also want our analysis to be sound in the end, so we need to think about how this solver and the update rule actually interact with each other. And here we have this theorem from the paper that a hosting solver with a sound update rule returns a sound result whenever it terminates. Now there's two terms here that we should probably talk about. The first one is hosting solver. What do we mean by this? Well, the first property is this thing that I mentioned. It's not supposed to modify this row itself, but always rely on the update rule for the updates. And the second thing is we need it to be robust in some sense with respect to the values of the row. So if the row always subsumes all latest contributions to the globals, then the solver needs to compute a sound result. This is the requirement that we have for a hosting solver. And then the counterpart is what do we require of the update rules. And there we say a sound update rule is one that if you have a sequence of calls to update globals, the returned updates, if you have any, will always subsume the latest per origin contributions. And whenever you have a contribution that's not already subsumed by row, you will produce an update. And then when you put these together, you get our final theorem. Now recall that our idea at some point was to apply widening and narrowing per origin. So let's see how this could be written as an update rule. And here we have this map, C map, where we borrow the static semantics from C. And the idea is that this is some internal state of the update rule, but it persists through the calls of the update rule. And in the C map, we record the last contribution that we have seen, and then whenever per origin, and then whenever we have a new contribution from some origin, we compare whether it is subsumed by the old one, in which case we perform narrowing, or if it is not, then we do widening. And then the new value of the row, or the update to the global, we obtain simply as the join of all of the entries. This looks a bit complicated, so let's do an example. So this is our example from earlier. We have, on the right, we have row, and on the left, we have the internal state of this update rule. So recall, we start the analysis somewhere here, and then our solver will call this update global with the origin U1 and this contribution of the interval 0, 0 to A. So we record this in our map, as we have not seen this contribution yet. And then to get the new value for A, we join together all of the things that we have in this map. So we produce an update with the value of 0, 0, and this then becomes the new value of row. Now at some point, the analysis continues inside of this loop. It will then read the value for this A, which is 0, 0. It will go through the branch, and it will produce a contribution from this origin U6 with this interval 1, 1. So we record this again in our map. Nothing too interesting. We join these things again together. We get the new value of the new interval of 0, 1. And then, of course, this A has changed. So later we will evaluate this loop again. And we will once again go in this guard. We will then find that now the contribution to A from this U6 is this interval from 1 to 2. So we take those two. As it's not subsumed, we apply a widening here. So we get an interval from 1 to infinity. When we join those two things together, we get the new interval for A that's from 0 to infinity. And then we do one more iteration. In this iteration, we will now take a look. We read the A, we apply the guard, and then we increase it by 1. So we will find that here the contribution from this local U6 is this interval from 1 to 10. And then now as this interval is subsumed, we will apply narrowing here, which gives us this interval from 1 to 10. If we combine them together, we end up with the interval from 0 to 10. And this is also the update that we produce. So we iterate the loop one last time, but we find that here we have reached a fixed point. So at some point, we then move on to the second thread. We read the value for A again. We check the guard. We find that here the contribution from this origin U13 to A is between -1 and 9. Now this is an entry that we don't have in our map yet, so we add it. We compute the new value as the join of all of the things. We have an update to this global A, and A has changed, so we reevaluate the loop once more. We go in here, we find that now the contribution is from -2 to 9, so it's not subsumed, so we need to apply widening once more. We end up with this value of -infinity to 9 in here, which gives us an update of -infinity to 10. There's also no new value of our A, and then we iterate one more time. Here we now find that actually this A is bounded, or the update to A from line 13 is bounded from below by -10. And now this value is subsumed, so we can apply narrowing again, which gives us this interval here. And if we join all of them together, we find out that the interval is actually the interval from -10 to 10. And then we would, of course, need to iterate everything one more time, but this is actually the fixed point that we wanted to reach. So what we have seen is we are able to do narrowing when the contributions from some origin shrink, which is nice. However, there's another problem that we encounter, and this is what we dub the problem of toxic trash. So consider this example program here. You have once again one global, and you have a sort of complicated loop in one thread, and the other thread you just check basically that the global has not been written. And here the problem is that while we are locally iterating and trying to find a solution, we do widening of this loop. So at some point we will consider this contribution of 42 to this global A. However, later on we will find that this is actually not reachable, this line 6. So the contribution that we have recorded for A is trash because we would not need it. And it's not just trash, but it's also toxic trash because it causes an assertion that we were interested in this thread to now fail. Now, how can one get rid of this toxic trash? And the idea actually here is surprisingly simple. It suffices to make contributions that are no longer happening explicit. So we basically wrap our update rule in another update rule that records for the last time when I evaluated this, which unknowns received contributions. And if now something doesn't receive a contribution anymore, I explicitly record a bottom contribution, which will then cause a narrowing and which will cause this toxic trash to disappear. So inside of the paper, we have several things. So what we've seen here is update rules that allow the values of globals to shrink. We have seen a form of abstract garbage collection to take out the toxic trash. In the paper, we also compare with an existing approach by Apines and colleagues, which was deeply intertwined with one solver that we casted as an update rule. We also give a detailed soundness theorem for the update rules. And we also consider the notion of properties that the update rules need to have to ensure termination of the analysis. And it turns out that there one needs an interesting property that is somewhat stronger than what you would usually have for a widening. The other thing we have in the paper is an experimental evaluation. So we do have a little bit of time to quickly touch on that. For our experimental evaluation, we implemented the update rules within the static analyzer Goblin, which is a static analyzer that targets real-world multi-threaded C programs, and it's based on abstract interpretation and side-effecting constraint systems. We did several evaluations. One of them was on context-insensitive analysis for this software verification competition reach safety benchmark set. And there we compared with a built-in strategy of the Goblin system, which is a little smarter than the strategy we've seen where we always widen, but not by that much. And we evaluated along two axes. One of them was the precision, and what we considered as a precision measurement here was something that we call the net impact. So we looked at the analysis results with the update rule and without the update rule and compared the abstract values of globals and locals. And we basically counted how many globals were improved, subtracted those where the result got worse, and then divided this by the total number of locals and globals that you have in the system. And we were quite happy to find that actually there is a net precision gain for 52% of the tasks. And for 20% of the tasks, it's also somewhat substantial. So it's more than 5% of unknowns that are actually improved. However, there's a downside. We also had a net loss for about 2% of the tasks. So in some cases, our smart update rule actually makes things worse. The other interesting metric is always how is the runtime. And here we found that the overhead was not too terrible. So we had a 3% average overhead over the baseline, which is a price you might be willing to pay to get more precise values for the globals. So to sum things up, we have seen that mixed flow sensitivity is a nice middle ground between flow sensitivity and flow insensitivity. We have seen that one can use update rules to decouple the handling of globals from the rest of the solver infrastructure. We have seen update rules that can recover precision. And we have also seen a technique for abstract garbage collection that takes out the toxic trash. And finally, we have taken a look at the experimental evaluation on SVComp. And in the paper, we also consider a large set of real-world programs. So with that, I'd like to thank you for your attention, and I look forward to any questions.
Questions?
Okay, thank you. So in your initial example, one other technique that could help improving precision would be to use some kind of, well, better widening, like for instance with thresholds or to find a way to widen a little bit more slowly.
Absolutely,
Did you
yes.
compare with such techniques and see where you do improve better or less, or when you can combine your technique with that?
So with widening thresholds specifically, we did not compare. The framework in principle supports them. However, here we were shooting for a general solution. And with this widening thresholds, it's somewhat hard sometimes to determine what the threshold should be. So here they were constants, but quite often they might not be constants. What we did compare with is a widening delay. So I think a widening delay of 3 or something, it also improved things, But then there was an additional improvement when we considered our update rules here.
Sure, thank you.
Another question?
I don't have a deep understanding of this analysis, but I have a naive question. So based on the experimental results, you have some improvement over the standard analysis implemented in the Goblin and some loss of precision.
Yeah.
If there is a way to combine these two techniques and to get best of both worlds.
There might be a way to combine these two techniques, yes. So it actually turns out that this precision loss, the case where we lose precision mostly goes away if we combine it with a widening delay. So basically the effect where we see these precision losses is due to the update rule, the default update rule in Goblin being a little bit smarter than the one I've presented here.
Yeah, I thought that maybe some way of improving precision would be to do some kind of policy iteration where you could do the analysis on one thread, widen on one thread, and then narrow on this thread. And then when we reach a fixed point, you can switch to the other thread, do the same thing. Can we describe your technique as a way of doing that, but without committing to a single fixed point strategy?
Yes,
how would it relate to that?
Yeah, I would think that the strategy you've described is an alternative strategy and it would work, but as you've said, it's somehow fixed to this fixed point strategy where you sort of locally iterate the thread to a fixed point. And
Session. Okay, so our final talk is by Dorian Leber. We're going to hear about some nice improvements to relational abstractions.
Thank you. So yes, today I'll present our work on a new relational abstraction domain, which is based on an extension of the union find data structure. And this is work that was done with my PhD supervisor, Mathieu Lemaire, along with another PhD student from my lab, Hichem Haïtelaha, and his supervisor, François Bobo. And so to show you a small example of how our new domain works, essentially we can run through a very simple input program here, where we build, we have a very small loop that we've initialized with two values 0 and 4, and as we step through the loop, we can learn relations between our variables. So here we'll learn that x1 is x plus 1 and y1 is y plus 1, and we can represent them in this term graph where our nodes are variables and our arrows are annotated by the relation between these variables. Now, as we get to the part where the loop repeats and we go back to the head of the loop, obviously we don't know the exact values of variables anymore, but the relations remain. And what's more, if we look at the two first iterations of the loop, we can actually deduce a relation between x and y because we know their constant values, and that relation is also preserved when we continue stepping through the loop. What that means is that when we exit the loop here, we have lost the exact numerical values of the variables, but we still have the relations between them. And now, of course, we can have an implicit assignment at the call side, but it's just equality, so we can also store that in our graph. Finally, we have another very simple assignment, and here we can prove the assertion because while this relation isn't stored directly in our graph, it's implied by our graph, and we can actually, one of the great strengths of the domain I'm going to show here is that it's very fast, and you can recover that kind of relation extremely quickly. So to give some more general context, in the general field of program verification, your abstractions, they generally fall on a spectrum where the more precise you want to be, the slower you are going to be. On the extremes on the spectrum, on one hand, you have non-relational abstractions, which are very fast, but they only store information numeric information for each variable independently. And on the other hand, you have the polyhedra domain, which stores linear relations like these between an arbitrary number of variables. And in the middle, you have weaker domains, which are also relational, but generally store a less generic class of relations. So you could have equality instead of inequality, or you could limit yourself to only 2 variables. And you have the well-known octagon domain, where you limit, not only do you limit yourself to 2 variables, but you also limit the coefficients to plus or minus 1. And where do we fit on this graph? Well, we're all the way over there. The idea is that we are faster than all of these domains, but we are even more restrictive on the relations we allow. So the general form is y equals f of x, where f is going to be some injective function. And for a nice practical example, we have the relation of y equals ax plus b. So to start, I'd like to give some intuition as to how we manage to be faster than all these other domains. And the idea is that the key performance cost in most of these domains is going to be transitive closure computation. So you have this generic theorem in abstract interpretation that when you have information, it's best to propagate that information as much as possible before doing any step for the program. And that can be very costly because, as you can see here, if I want to propagate the information I have between my variables to deduce a relation between x and t, I have 2 possible paths. I can either go through y or z or just through z. Do I need to explore all my possible paths? And exploring all paths with graph, well, that's a Floyd-Warshall algorithm, that's cubic complexity. It's fairly expensive. And that leads us to the key assumption of our paper, which is, what if we didn't have to compute such an expensive transitive closure? And so we're going to assume that the relation is going to be the same on any path. And that way, well, first of all, we can shrink our graph. We can only maintain a spanning tree, because thanks to the assumption, we know we're not forgetting anything. And we also know that we can recompute the value between 2 arbitrary variables very fast, because we just need to look up a single path. Now, there are some quick consequences of that assumption, because it is a very strong assumption. One is that just by reasoning a bit about the shapes of our graph, you'll notice that the composition of relations along our graph edges are going to be associative. They're going to have neutral elements whenever there's a loop, and partial loop paths are going to act as mutual inverses. And therefore, a very natural follow-up assumption is that these relations have a group structure. And this is what we're going to assume because it simplifies the rest of the presentation. But now I can finally present the labeled union find data structure. So as I mentioned, it's an extension of union find. And the idea is we just add these labels, these relations, to the edges of our union find. And the key operation we have is the find, which is that for any connected component in our graph, we can return 1 distinguished element. And we're just going to modify the find to also add, to return not only the distinguished element, but the relation we have with that distinguished element. So if you call it on an element that has no parent, like R, you return R via the identity relation. And if you call it via to any other element, well, you just follow the arrows to the parent, composing relations as you go, and return that. And one key feature for performance in union find and in labeled union find is that whenever you do more than one composition, you can perform this path compression, which you change the pointer from y to point directly to the representative. That way you flatten your structure, and any subsequent calls to find will be much faster. But of course, find is kind of an internal technical operations. From the abstract domain point of view, what we care is finding queries like, if I have 2 variables, do I have a relation between them, and adding new relations as I go, of course. So get relation is actually very simple. It's implemented using find. You just call find on each of the variables in your query, and you look if they have the same representative. Then you want to create a variable between them. And here, to get from z to x, well, you go from z to r, and then the inverse of from x to r. And of course, if you have a separate cluster with a different representative u, and you want to find the relation between z and u, you call find on both of them. You realize they don't have the same representative, and so you know there is no relation. Now, when it comes to adding a new relation, well, it actually proceeds in exactly the same way as you would in normal union find. You find the representatives of both elements. So this is what the union operation would be in union find. We've called it add relation because it's a little more complex than just a union, but the idea is just the same. You go to the representative and you add an arrow between the representatives. And the idea is as to what label you need to put the arrow. Well, what's the path you do know from R to U? You know you can get from R to Y, you know you can get from Y to V, and you know you can get from V to U. So you just compose all 3 of these. So yeah, that sums up the data structure. It's a rooted forest with group operations on the labels, and you have these 3 functions to manipulate your data structure. And one very important fact of these domains is that all three of these functions have amortized constant complexity, so it's a really fast domain. And now I'm going to talk a bit more about using labeled union-find in program analysis. So we want to use it to represent relations, abstract relations between variables. And well, a natural question that comes up is what kind of relations are suited? Because when you look at the requirements we have, well, we want to represent relations, so our union-find labels must concretize to actual mathematical relations between variables, but they must also be a group. And what we found is that the combination of these two requirements essentially means our relations have to be injective functions. So for example, you can't use interval difference, which I've shown in the previous slides, because that's not injective, but you can use constant difference, which is y equals x plus b. You can also use two-variable linear inequality, y equals a x plus b, as long as you have a not 0, obviously, and your coefficients have to be either rational or 0, because you need to be able to invert the relation. You can have modular multiplication, because on bit vectors, if you multiply by an odd number, you can actually invert that. And for a more bitwise operation, you can also do things like this XOR and rotate relation. Obviously, both XOR and rotation are injective functions, so their composition is as well. And actually, our requirement is a bit weaker than what I've just said. It's not injective functions between the variable values, but it's injective functions between equivalence classes of the variables values, which allows us to have things like this parity comparison relation, which just says if the variables have the same parity or not. Obviously, that's not injective on the whole space of possible integers values, but it is possible on integers quotiented by modulo 2. And another nice fact about label union-find is that it can combine easily with other domains to help factorize them. So essentially, suppose you have a term graph like this, and you want to store numeric information about all your terms. That can get quite redundant, because if you know the value of y, then you can deduce the value of y plus 7. You don't actually have to store it. So with labeled union-find, the idea is very simple. You just store one value at the representative, and then for elements of the class, you can deduce the value. So say if you want to find out the value of y plus 7, you call find on y plus 7, you find its representative, you find the relation it has to this representative, and you look, well, 0,4 is the value at the representative. I update it via my relation plus 7, and I get the value of y plus 7. Said value works very similarly. This time, suppose I learn that 2y is in the interval minus 4, 4. I find the representative, and I shift my interval. This time, there's the inverse of the relation, because I'm taking the edge in the opposite direction. And then I can intersect it with the previous representative's value. And then, of course, I can propagate to subterms and superterms. And already we can see a little improvement of using this domain is because we've factorized our graph, we've essentially reduced the number of nodes. This propagation step will be faster. And so formally, this is done via a function a, which takes a relation, a value, and returns the updated value. And what we found is that this a function must be compatible with the group operations on relations. Essentially, if I want to shift a value via the identity relation, then I must return the same value unchanged. And if I shift a value multiple times via a succession of relations, it's the same thing as if I shifted the value once via the composition of these relations. So A must be a group action. And that actually implies some interesting facts, essentially that the relations we use, the abstract relation we use in our graph, and the abstract values we have on our nodes must be compatible. So for example, if I want to use a constant offset relation with intervals, then I do have an exact action because addition on intervals is exact. If I want to use the TVPA relation with intervals, it is exact as long as I'm working with reals or rationals, because if I'm working with integers and I say I multiply by 2, then I've increased the size of my interval and therefore I've lost precision. For an example where that doesn't work, if I want to use constant offset or TVPO with a bitwise abstraction, so an abstraction which stores for any number, either it's 0, 1, or each bit of a number is either 0, 1, or unknown, well, you can notice that just by adding 3 to this very simple abstraction of 0 or 1, I get 8 possible values at the end. So I've lost precision, and using such a bitwise abstraction with constant offset will lead to precision loss. But of course, that bitwise abstraction works very well with the XOR rotate abstraction, because these XOR and rotate are both operations that can be precisely encoded if you have the bitwise representation of some number. But on the flip side, the XOR rotate relation does not work with intervals. And so this this factorizing of other domains, so I've presented it for non-relational domains, but you can also do it for other relational abstractions. So for example, if you have an octagon domain, which tells you facts like z plus x is smaller than some constant, and you also know that y equals x plus b, well, you can just shift that relation along that and learn a similar octagon relation between x, z, and x, and y. And that is actually very interesting because a lot of these weakly relational domains, they have supralinear costs in the number of variables they store. And so being able to factorize this and store fewer relations because you only store relations with one element of the class and then you shift them to deduct them from the others, you've shrunk the size of your variable space, and so you can gain some very nice precision gains. For another more complex examples, you can use that to eagerly discover all identities in your union finite graph. This one's more involved. You need to store a map at the representative, which is sort of an inverse map of the union find, and therefore it comes with an extra overhead, but it's still very cheap, and that way you can easily discover all equalities no matter which order you put them in. And one last point I want to touch on here is what happens, well, a limitation of union find you might notice is that in abstract interpretation, we like our states to be immutable because whenever we hit control flow split, we want to be able to copy the state to study each branch independently and then join their different values at control flow join. And of course, union find is a very mutable heavy structure. It relies on pointers, it relies on mutating data, and copying the whole thing could be quite expensive. And so one solution we found, which works a lot better than you might think, is only store in flow insensitive relations, because that way I only store things that are true everywhere in the programs. I don't need to copy my state, and I don't need to join my state. It kind of sidesteps the problem, but especially as we had a paper last year where we showed we could compile a program to an SSA form as part of our analysis, and that compilation is very nice because in the SSA form you tend to create new terms whenever you learn more information about variables, especially at control flow joins, and that way you have a lot more flow insensitive relations because you have all these extra terms to handle. So for a very simple example, obviously it's when I built, if I have a term e and then I have e plus a constant or e times a constant, I can obviously build a relation. So for the join, which is what the SSA represents with these phi terms, if I have one branch where I have a linked to b via a relation and another branch where I have a linked to b via the same relation, well, obviously these phi terms will also be linked via the same relation. And another interesting case is when I join constant pairs. So if I know I have a branch where x equals 2 and x equals 4 in the other branch, y equals 1 on one side and y equals 3 in the other branch, then I can actually find a relation between them. It's just finding a line between 2 points in 2D space. You can always do that. Of course, this is specific to the TVPA relation, but for other relations, you can usually find a value that matches an arbitrary constant pair. And these might seem cherry-picked examples, but they are sufficient to show the example I've shown in the beginning, or this one, which is essentially the same but simplified. It's when you have simultaneously increasing loop counters, because if you run a non-relational analysis on this guy, what you'll find is that you have a precise value for I, because you're going to identify that I is a loop counter, and so narrowing will be able to reduce it to a precise value, but you won't get a precise value for j. However, with labeled union find, on your first iteration through the loop, you'll know I is 0, j is 4 on the side. Well, before the first iteration. After the first iteration, I is 1, j is 3. That way, no, not 3, 7. That way you can deduce that j equals 3, I plus 4, and in subsequent iterations, that relation will be maintained. So at the end, you can get a precise value of j from the precise value of I. So yes, to conclude, I've presented the labeled union find data structure, which is an extension of union find, which adds labels to the parent edges, and with the requirement that labels must have a group structure. And then I've shown how you can use that data structure to represent a very efficient weakly relational domain, thanks to the very fast transitive closure computation. Of course, this is limited to injective relations that form a group, but as we've seen, it can combine with other domains to essentially shrink the space of variables the other domains have to consider. Now, this has been implemented both as part of the Codex Static Analysis Library, so an abstract interpretation library, and a Colibri2 constraint solver. So we already have two slightly different use cases, and you can check out the artifact or the paper if you want to learn more about the implementation. And finally, yeah, we have some postdoc positions, so if really interested by our work, feel free to contact my supervisor.
Okay, questions?
Thank you. How do you compute abstract unions or widening or approximation of pairs of abstract states?
So the idea, is that we only store relations that are true everywhere, so we don't really need to widen. And part of that is handled by the SSA state, which will create new terms upon widening, and these new terms won't have the relation they used to have if we can't show that they hold on both of the values.
Okay, so you don't have any widening or abstract union?
We have a join. As I mentioned, we mostly focused on the imperative version because it's faster, but we also have a functional version of union find, and we do have a join operator. It's a bit complex. It's detailed in the annex of the paper. But essentially, the key algorithm for the join is that we use Patricia trees to represent our union find pointers, and these Patricia trees allow us to get to the diff of two states in n log d time, d log n time, where d is the difference and n the total size. So you don't have to explore the whole state space. You can get the diff relatively faster.
And is it optimal in terms of precision, or is it approximate?
It is optimal in terms of precision. We've shown that we don't lose anything, yes.
Other questions? I had a question. I was just trying to understand. So is this as precise as octagons? Or what is the precision relationship?
It's not as precise as octagons because we store weaker relations. But yeah, the argument on my little speech at the beginning is that we're much faster than octagons because we don't have the cubic closure to compute.
So do you vision the practical application would be to store certain relationships maybe in a flow-insensitive manner using your new data structure, but then also retain octagons for things that you need to track flow sensitively or some other abstract domain?
Yeah, yes, like I mentioned, one of the interesting aspects is that the combination with other domains where you can shrink the space, and essentially you could have octagons between your different variable classes, but because you've grouped variables in classes, you have fewer variables, and therefore your octagon domain is faster.
Got it. Okay, another question.
At least I know that the union find can be implemented in the consistent way or persistent way without using mutable features, using a rank optimization. So why didn't you use a rank optimization instead of the path compression?
You're talking about persistent arrays, that kind of data structure?
I'm sorry?
Are you talking about persistent arrays?
Persistent union find.
And these use persistent arrays inside. So actually, this is funny because if you asked the question 2 weeks ago, I'd have given you a different answer. I initially thought that would be very bad because persistent arrays, essentially you only have one copy at a time. So they're fine when you're just going down a branch and then going down the other branch, you just have to roll back. But when you want to do the join, you have to go back and forth between both of your branches, and that's actually quite expensive. So that was my initial reasoning for saying we can't use persistent arrays. What I've started to realize is that a key ingredient as to why the join isn't completely too expensive to compute is that we can find the diff quickly. And maybe we could use a variant of persistent arrays where instead of going back and forth to check the values of each state, you just do one pass, accumulate all the diff, and then use that to create your join. It's just an idea. I haven't tested it or implemented it in any way, but it might be worth checking out.
Okay, let's thank the speaker again. Let's thank all the speakers.